Hey everyone, so we're looking at section 6.4 today, and this is the last section in chapter 6 that we're going to be talking about. And as you can see, this section goes over the normal approximation to the binomial distribution. So we're basically saying a normal distribution is often used to solve problems that involve binomial distributions, since when n is large, you can say about 100, calculations can be too difficult to do by hand when we are using the binomial distribution. So remember, in chapter 5, we talked about the binomial distributions, and they had these following characteristics. Of course, they should have a fixed number of trials. The outcome for each trial must be independent. For each experiment, there should be only 2 outcomes, or we should be able to reduce them down to 2 outcomes. And of course, the probability for the success should remain the same for each trial. Now, another thing you should remember is that a binomial distribution is determined by n, which is the number of trials, and by p, which is the probability of success, right? So we are saying when your p, the probability of success, is approximately 0.5, and as n increases, which means your number of trials increases, we say that the shape of the binomial distribution will become similar to the shape of the normal distributions. Okay, so again here the probability of the success has to be approximately 0.5, and your n has to increase. So basically the idea is the larger n is, and the closer our probability or p-value is going to be to 0.5, the more similar the shape of our binomial distribution is going to be to that of the normal distribution. Okay? Now, what happens if your p-value is closer to 0 or 1 and n is relatively small? So, of course, as you can imagine, since this doesn't meet the conditions of p being approximately 0.5 and n being a larger number, so if your n is relatively small and the probability is close to 0 and 1, that means we cannot use normal approximation because it will be inaccurate. So we are saying, as a rule of thumb, statisticians generally agree that a normal approximation should be used only when your n times p and n times q values are both greater than or equal to 5. So when you multiply n times p and you get a number which is 5 or larger than 5, and same thing with n times q, if the number is 5 or larger than 5, then you can use normal approximation. And remember, we calculate q by doing 1 minus whatever that probability p comes out to be. So just as an example, we are saying, okay, what if p is 0.3 and our number of trials is 10? When we multiply n times p, we only get the answer 3, right? So in this case, since our n times p is not 5 or greater than 5, we should not use a normal distribution as an approximation here. However, if let's say our number of trials is 10, n times p comes out to be 5, and in this case n times q will also come out to be 5, obviously we can go ahead and use normal distribution as an approximation. So just to show you, this figure on the left is where we are taking n as a value of 10, p as a value of 0.3, and you will notice this is what that binomial distribution will end up looking like. And you can see it's kind of tapering a little bit to the right. So this is more right skewed or positively skewed, right? So this is where you can see the shape of our binomial distribution is nothing like our normal distribution. But when you look at the binomial probabilities for n equals 10 and p equals 0.5, you can see that distribution has a symmetric shape and looks more like a normal distribution than the one on the left. So on the one on the right, we can use a normal approximation for it. So that's the difference between these two examples that we talked about over here. Okay? They are also saying, in addition to our previous condition of n times p being greater than or equal to 5 and n times q being greater than or equal to 5, we also have to use a correction for continuity. We are doing these normal approximations. So your correction for continuity is basically a correction employed when continuous distribution is used to approximate a discrete distribution. So continuous distribution would be your normal distribution, and discrete distribution would be your binomial distribution. So they're basically saying you have to use this correction whenever, in our case, you are using a normal approximation for a binomial distribution. Okay, and this would of course be true for any continuous distribution being used for a discrete distribution. Okay, so your continuity correction basically means that if you have, let's say, a specific value of x equals 8, in this case, instead of using x as the value of 8, we would use the boundaries of that value, which means we would be using the values going from 7.5 to 8.5 instead of using the number 8 directly. So remember how we had talked about calculating boundaries. We looked at it in chapter 1, we looked at it in chapter 2 when we were drawing our histograms and coming up with our frequency distributions. Okay, so basically they are saying when you employ a normal distribution to approximate the binomial distribution, you must use the boundaries of your specific values of x, as we are showing you here in this table right over here. So they are saying, for example, if you are trying to find the probability of your x value being exactly equal to 8, the correction factor is actually going to be finding the probability of values going from 7.5 to 8.5. Now, if they were asking us to find the probability that x will be less than or equal to 7, then our correction factor in that case would be probability of values of x being less than 7.5. If they were asking us to find the probability of x values being greater than or equal to 3, in this case, of course, our correction would be at the probability being greater than 2.5. So this table over here lists 5 different cases based on what probability you are being asked to calculate, and then this would be coming from the binomial distribution. So in normal distribution, we would have to use these values. Okay, so we have to remember to use that correction factor, and then of course we need to use the calculation of our binomial distributions calculations for mean and standard deviation. So mean is n times p, standard deviation is the square root of n times p times q, or basically you can deviation was n times p times q, and when we take a square root on that, we get our standard deviation. So remember, whenever you are going for a normal approximation for a binomial distribution, your mu has to be n times p, sigma is square root of n times p times q, and you want to make sure the n times p value is greater than or equal to 5, and n times q value is also greater than or equal to 5. So the first step will always be to check and see whether we can use the normal approximation or not. If you can use normal approximation, then find the mean and the standard deviation using these formulas from the binomial distribution. They are saying write the probability in your probability notation using x. So this is where you do p of x equals a number, or p of x is greater than equal to a number, p of x is less than equal to a number, any of these cases right over here that you saw in table 6.2. Okay, then they are saying rewrite the problem using the continuity correction factor, and then of course draw your little curve to see which area we are looking at. Once of course you have your correction factor taken care of, find your corresponding z values, and then of course find your solution. So these steps is what's going to be involved in this normal approximation for our binomial distribution. Okay, so let's take a look at this first example over here. They're telling us it has been reported that last year 25% of the drivers have fallen asleep at the wheel. If 200 drivers are selected at random, find the probability that 62 will say that they have fallen asleep while driving. So they're giving us the probability of drivers who have fallen asleep as 25%. So that's the probability of 0.25. Remember, your Q is 1 minus P. So if you just did 1 minus 0.25, you get the value of 0.75. So that's where they're getting this Q value of 0.75. And of course, we're talking about a random sample of 200 drivers. So that's where n equals 200. So the first step is checking to see if we can use normal distribution or not. So n times p, when we multiply that, we get 50. N times q, we multiply and get 150, right? So remember, our n times p has to be greater than or equal to 5, and n times q has to be greater than equal to 5. So both of these conditions meet, which means we can use normal distribution. So once you have that, find the mean and standard deviation. Mean is n times p, which is 50. Sigma is a square root of n times p times q, which comes out to be 6.12. Now, you actually do the mean calculation right over here where you are checking in the first step. So you've already taken care of the mu. So really just bring that number down here and then find your standard deviation. Now the question is asking us, finding the probability that exactly 62 will say they have fallen asleep while driving their vehicle, right? So in this case, since they only gave us the number 62, they did not say less than, more than, at most, at least, nothing like that. So we know they're talking about exactly 62. So that's why your probability notation is going to be finding the probability where your x equals 62. So now, once you come up with that, then we go to our table, and you can see for x equals a given number, your correction factor right here in number 1 is going to be using the boundary half of that number and half a point above that number, right? So just looking right here at this first case. So that is why from the number 62 we are subtracting 0.5 and adding 0.5. Okay, so to calculate our boundaries, we subtract 0.5 and we add 0.5. So basically our correct going to be finding the probability between 61.5 and 62.5. So of course, we go ahead and do our little normal curve over here and show the shaded area. So even though we are trying to find the exact value of 62, with the correction factor going from binomial to normal distribution, we have to use this correction factor. So you find the z-values for both of these numbers. So starting with the first z-value using 61.5, we are coming up with a z-value of 1.88. For z2, which is 62.5, we come up with a z-value of 2.08. And now we need to see what those probabilities are going to be. So again, you can just go to your table. That's the wrong one. Okay, so let's check for 1.88. So 1.8, and we are going to 88. So that is going to be 0.9699, and you can verify that right here. And then for 2.04, okay, 2.001234, it's going to be at 0.9793. And there you go. Okay, so that's how you come up with those. And then since we are talking about in between these two values, of course you go ahead and subtract them, and we are looking at a probability of about 0.94. So close enough to 1%, but we'll keep it at 0.94. So we are saying basically that the probability that exactly 62 people will say that they have fallen asleep at the wheel while driving is basically less than 1%, 0.94%. Okay, so this is where we are using this idea of binomial distribution, but using normal distribution as an approximation. Okay, all right, let's look at another example over here. So they're telling us 10% of Americans are allergic to ragweed. If a random sample of 200 people is selected, find the probability that 10 or more will be allergic to ragweed. So of course they're telling us 10% is the probability. So that's P equals 0.10. And then of course to find Q, we do 1 minus P, which is where you get Q equals 0.90 from. They're telling us we have a random sample of 200 people, so that's our n value. Now to check our answers, we multiply n times p, thus a value of 20. So as long as your n times p is greater than equal to 5 and n times q is greater than equal to 5, we can use normal distribution. So of course you can see we get 20 and 180 as our two answers. They're both numbers larger than 5, so we can use normal distribution. So find the mean and standard deviation. So your mean comes out to be 20, which we just calculated, and then sigma, standard deviation, would be square root of n times p times q, which comes out to be 4.24. Now our question is, find the probability that 10 or more people will be allergic to ragweed. So putting this in our probability notation, we are saying 10 or more people being allergic to ragweed. So we need to do our little continuity correction. So let's go back to our table over here, and this is p equals x is greater than or equal to, so this is case number 2 over here. So our correction factor is going to be probability of x greater than a minus 0.5. So our correction factor here is going to be probability of x being greater than 10 minus 0.5, or basically probability of x being greater than 9.5. So if you think about 9.5 being here and we're talking about greater than, then this would be our shaded area that we're trying to find the probability for. Okay, so find your continuity correction factor, and then of course do your little diagram. Now we're ready to find our z-score, so that's going to be for the 9.5 value. So that z-score comes out to be negative 2.48. So let's take a look at it. Negative 2.48, and looks like this number comes out to be 0.0066. So that's your probability, but this is of course going to show you the less than, right? So it's going to be this little tail end over here, which has that probability of 0.0066. So to find the probability to the right, this is of course we do 1 minus that probability, and that gives you an answer of 0.9934 or 99.34%. So we are saying in a random sample of 200 Americans, the probability that 10 or more Americans are allergic to ragweed is going to be 99.34%. So you can see again how this example works out with our normal approximation for binomial distribution problems, okay? Okay, so let's look at our next example over here. So they're saying if a baseball player's batting average is 0.320, so you can think of that as 32%, they are saying find the probability that the player will get at most 26 hits in 100 times at bat, right? So again, of course, our probability is p equals 0.32. You do 1 minus p to get the q value, which is where we get the 0.68 from. And of course, they're talking about 100 times at the bat, and the player gets at most 26 hits. So of course, your n is 100. So to check our values to see if we can even use normal approximation, n times p gives us the number 32, n times q gives us 68. So again, both n times p and n times q are greater than the number 5. We can of course use normal distribution over here. So we've already got our mean calculated. Calculate the standard deviation, and in probability notation they are telling us at most, which means the maximum number of hits the player can get is 26. So of course that that probability notation you are looking at is p of x being less than or equal to 26. So for our continuity correction, let's go back to this table over here, and this time we are looking at the p-value being less than or equal to 26. So you're looking at case number 4. So this is where you take the your value and add 0.5 to it. So you will see we have taken for our continuity correction the value of 26 and added 0.5 to it. So that means you're looking at P, the probability of X being less than 26.5, and then of course look at the area under our normal curve. So this is the shaded area that we are trying to find the probability for. So let's go ahead and find our z value, which is going to be for 26.5, and that z value comes out to be negative 1.18. So negative 1.18 is going to give us the probability of 0.1190. So there you go, 0.1190. So that's giving us the probability of approximately 11.9%. So we are saying the probability that a player gets at most 26 hits in 100 times at bat is going to be a probability of 11.9%. Okay? Alrighty. So this last example here is basically just talking about the closeness of the answers you get from a normal approximation compared to the binomial distribution here. So here they're telling us, okay, let our n value be 10, p equals 0.5, and then if you use the binomial distribution table, which is table B in appendix A, you can find the probability when x equals 6. Okay, so n equals 10, x equals 6, and our probability is 0.5. So let's take a look at this. N equals 10, x equals 6, and our probability is 0.5. So you can see these lines are going to meet at this probability of 0.205 over here. So that's where, using that table, they're getting this probability of 0.205. Now if we do a normal approximation on these values, we want to see how close do we come to this approximation of 0.205. So again, if you multiply n times p, you can see you are getting the value of 5. If you multiplied n times q, you would also have 10 multiplied by 0.5, which gives you the value of 5. So of course we can use normal approximation on this, find your standard deviation. Now here, since we're talking about the probability of being x equals 6, with our continuity correction, you would be going for values from 5.5 to 6.5. So that's why we are finding the two z values for 5.5 and 6.5, which comes out to be 0.95 and 0.32. So for 0.95, so 0.95 is giving us the value of 0.8289. So there we go. And then for 0.32, 0.32, we have a probability of 0.6255. So 0.6255, again, go ahead and subtract those two probabilities, and we are getting an answer of 0.2304. And you can see that is pretty close enough to that probability of 0.205 that we got from our binomial distribution table. So it's a very close number over here. Okay, and that's of course the shaded area we are talking about if you put this under a normal curve for this example. Now you can also use your normal approximation with other distributions, and that could be, you can think about the Poisson distribution also, though we're not talking about it. Just be aware that other than binomial distribution, your normal approximations can also be used on other types of distributions. Okay, so these were the examples. Now let's go ahead and take a look at some examples from our textbook. Okay. Alrighty, so let's look at our first example here that we want to talk about, and it's number 16 over here. So they're telling us that college students often make up a substantial portion of the population of college cities and towns. So in State College, Pennsylvania, it ranks the first with 71.1% of its population made up of college students. And they want to know what is the probability that in a random sample of 150 people from State College, more than 50 are not college students. Okay, so our event here is talking about more than 50 people will not be college students if we select 150 randomly. So what's happening here is they're giving us the probability of what is the population that makes up college students. If you're talking about your probability of finding that more than 50 of these people randomly selected are not college students, that actually means that 71.1% is going to be the probability of the failure. That's your Q value. And to find the P value here, we would have to do 1 minus Q. So basically, like I said, think of 71.1% as being the Q value, because that's not the probability we're interested in. We're interested in what population of this city is not college students. So that's going to be 1 minus 0.711, which will give us the probability. So if you look at that calculation, it's actually going to be, so that 71.1% becomes your Q probability, and the P probability over here was basically taking the value of 1 minus Q, so that was 1 minus 0.711, and that's how we came up with 0.289. Now they're telling us we are randomly selecting a group of 150 people. So the first step we have to do is to check and see if we can use normal approximation or not. So this is where we multiply n times p and n times q and see what values we come up with. So we are doing 150 times 0.289 and then 150 times 0.711, and these answers will come out to be 43.35 for n times p, and for n times q we end up getting 106.65. So you can see both of these numbers are larger than 5, so we can use normal approximation over here. So that means our next step is going to be to find the mean, which we've already calculated because that's n times p, which was 150 times 0.289, and that comes out to be, and I'm going to round this answer to 1 decimal place, and that comes out to be 43.4. If you leave it as 43.35, your answer will be slightly different because of decimal approximations. And let's find our standard deviation. Okay, so this will be standard deviation, and that will be square root of 150 times, that should be 0.289 times our Q value, which is 0.711. So when we multiply all of these together and then take their square root, approximately our standard deviation, and again I'm going to round this to 1 decimal place, it will come out to be approximately 5.6. Okay, alrighty, so we found the mean, we found the standard deviation. Now let's do our probability notation, and the question was asking us what is the probability that out of the random sample of 150 people, more than 50 are not college students. So this one we are saying more than 50 are not college students. So remember, you have to use the continuity correction factor over here. So let's go back to the table. Okay, there we go. So this is going to be just p greater than 50, so that means you're going to add 0.5 for our correction factor, so that's going to be x greater than 50 plus 0.5, and again you are looking at, not this guy, you're looking at case number 3 over here. Okay, So case number 3 is what we're using. And of course this comes out to be the probability of x being greater than 50.5. So let's take a look at our normal approximation here. Our mean value is at 43.4, and this is for greater than 50.5. So we're looking at this area over here. Okay? Alrighty, so the first thing we have to do is find our z-score for 50.5 minus the mean. And our mean value is 43.4, and then we're dividing this by standard deviation, which is 5.6. And let's see what kind of z-score we end up getting. So 50.5 minus 43.4 divided by 5.6, and looks like we're getting, again rounding this to 2 decimal places, we will have 1.27 as our z-score. Okay, 1.27. So let's see what that comes out to be. 1.27. So there we go. 1.2 and 7 is coming out to be 0.8980. So this is the area of 0.8980. Just verifying my number. 8980. Now, of course, this is always going to be the less than value. We're interested in the greater than. So that means for our greater than, we would have to do 1 minus 0.8980, and that will come out to be 0.102, or basically 10.2%. Right? Okay, so we have our probability for x being greater than 50.5. So we are saying this is going to be 0.102 as the area, or in probability 10.2%. So we are basically saying if you have a random sample of 150 people from State College, then our probability that more than 50 people are not college students will be 10.2%. So let's go ahead and write that down. So in a random sample of 100 people from State College, Pennsylvania, the probability that more than 50 people are not college students is 0.102, or 10.2%. Okay, so as I said, if you did different rounding for your mean and standard deviation, then this answer can come out to be slightly different, because of course your z-score will come out to be different, which means your probability value will come out to be different. Okay, but this is the general steps that's involved in calculating these normal approximations for binomial distributions. Okay, then the next example I wanted us to look at is number 20 over here. And number 20 is saying, according to the U.S. Census, 67.5% of the U.S. population were born in their state of residence. So if we have a random sample of 200 Americans, what's the probability that fewer than 125 were born in their state of residence. Okay, so let's go ahead and take a look at this. I've already got all the numbers written down over here. So of course the first step we want to do is check and see if we can use normal approximation. So we multiply n times p, which is 200 times 0.675. And that comes out to be 135. Now let's do n times q, which is 200 times 0.325. And this will come out to be 65. And again, both numbers are larger than 5, so we can use normal approximation here. So of course the first thing we do is find the mean, which is our n times p value, and we've already done this calculation. And this comes out to be 135. Now let's do standard deviation. So that's sigma square root of n times p times q. So that's 200 times 0.675 times 0.325. So multiplying all of these and then taking their square root will end up giving us approximately, and again I'm going to round this to one decimal place, so we'll round this to 6.6 as our standard deviation. Now let's do our probability notation. So the question is asking us, and this is number 20, what is the probability that fewer than 125 were born in their state of residence? So fewer than 125 means x is less than 125. So do our continuity correction. When we are saying x is less than a number, you're using case 5 over here, which means you are subtracting 0.5 from this number. So that will be 125 minus 0.5, which will of course give you a probability of x less than 124.5. Okay, so that means our mu here is 135, and we're looking at the probability of x being less than 124.5, so that's this area over here. Okay. Alrighty, so let's see what this probability comes out to be. We need to find our z-score. So that's 124.5 minus 135 divided by sigma, which is 6.6. And this z-score, okay, so we subtract the numbers on the top, divide by 6.6, and our rounded answer is coming out to be negative 1.59. So let's see what area this gives us. Negative 1.59, negative 1.5, and then 9 would be the very last value, which is going to be 0.0559. So 0.0559. Okay, and since we are talking about less than, you don't have to do any calculation here. This just comes out to be 0.0559, or as a percent, this would be 5.59%. So this is what we are looking at as our answer. So this area is 0.0559. Okay. Alright, so basically just to put this all in our conclusion, we would basically say in a random sample of 200 Americans, and their question was, what's the probability that fewer than 125 were born in their state of residence? So we would say the probability that fewer than 125 were born in their state of residence is, and we had what, 0.0559, or basically 5.59%, right? So if you took a sample of 200 people and you asked 125 of them, or at least less than 125 of them, there's only a 5.59% probability that they were born in their state of residence. Okay, so again, you can see it's a pretty straightforward process here, but just make sure you are following all the steps and going about your calculations accordingly. So this was example number 20, and basically this is what we are looking at over here. Now I will have a couple more examples for us to work through class, so just make sure you look through the handout, look through the video, and if you have any questions, let me know. Okay, so everyone, be safe, be careful, and I will see you in class next time. Take care. Bye-bye.